Live on TikTok for Math Thursday. All my students were also asking for a, if they could be on the TikTok live on Thursday from the bus. Like, actually, I think we'll be home by then.
Oh, are we going live?
Probably.
Oh, great.
Depending on how the trip goes.
Absolutely.
And depending on...
I was presuming it was off next week, but like
because usually we're back by like 7.
Yeah, I'm totally stoked to do it, of course. Great. We're live on YouTube.
Lovely.
And are we live on TikTok?
Yep.
Cool. I'm going to go post and monitor downstairs, and I'll be back in a second.
Okay.
Hello, yeah.
All right, guys. All right, we got a little simplifying exponents here for you. So go ahead and pop it in the chat what you think it is. And then this will kick us off for talking about exponent rules. And if you have any questions or anything like that that you're working on, any quizzes or tests or anything coming up that you're just not feeling great about, go ahead and put it in the chat, the topic. So we tend to focus mostly on like algebra 1 to algebra 2, kind of geometry, a little bit of pre-calc stuff in here. But we don't really get into many calculus concepts. But if you have anything in middle school math, great, let's do that, right? Fractions, decimals, all that kind of stuff. All right, so when we're looking at these, we've got we got to talk about some exponent rules, right? So we've got these exponents going on. We've got 4x cubed y squared z over 2x squared yz to the 4th. So when we're looking at this, okay, we've got some ideas. Okay, those are looking pretty good. Okay, so we want to see, so first thing we want to do is I like to really just work left to right. Now, if you're going to work left to right, what I would also recommend is if you are given a problem where they're not in the same order, like X, Y, Z or A, B, C or whatever, move them around so you are looking at them all kind of in the same sort of like terms, kind of. It's not exactly like terms, but same variable, things like that, right? So 4 over 2 becomes 2. Okay, so I'm going to keep track of what's on the top and the bottom. Okay, and we're going to look at these as fractions, right? So they're going to kind of simplify down. So x cubed over x squared. If we think about our exponent rules, right, we would subtract 3 minus 2, which is 1. But we can also think of it as these two x's down here cancel out 2 of these x's up here. So this goes away, and that becomes 1. Okay, no x to the 1 power or anything to the 1 power is just itself. So this is just an x. Okay, so y squared over 1, or sorry, y squared over y to the 1, right? This one cancels out one of those. So we've got y to the 1, but we don't have to write the 1 because it's right there. Then we've got z, we've got one of the z's on top and 4 on the bottom. So now this one cancels out down at the bottom, and it just cancels out one of them. Or you can look at 1 minus 4 would give me -3, which means it goes on the bottom. So this, I've got 3 z's left on the bottom. So there, we've got 2xy over z to the 3rd. Yay! Got a couple of right answers in there. Excellent. You should be very proud of yourselves. Right? So we're looking at, so there's a few different ways to kind of work this out. You can think of it with the exponent rules where you're subtracting with the division, or you can think of it as just kind of like canceling out, right? And actually canceling out the exponents or canceling out the variables is where that division rule comes into play and where it kind of all comes from, right? Okay, so we've got, is that 2i? I wish they taught calculus like this. I mean, a lot of this is getting into calculus. So, Cole, is that 2i and 6? Oh, I think, yeah. 2i minus 3 plus 6i squared. Okay, so I is a really interesting thing. So the lowercase I number or value, I guess. So I by itself is an imaginary number, and it stands for the square root of -1. Okay, Nicholas, yes, I can do geometry. If you stick a comment into the chat, I can work through whatever you want to work on. So I squared would be the square root of -1 times the square root of -1, right? Which becomes -1. Okay, I cubed is going to be root -1 times root -1 times root -1. So this becomes, let's see, this is -1 times root -1. So it becomes negative root -1, or negative I. Okay. And then I to the 4th is root -1 times root -1 times root -1 times root -1. So this is -1, and this is -1. So -1 times -1 equals +1. And then it becomes a cycle. So the interesting thing about I, and I to like powers of I, is it repeats. So if you have like I to the 5th, right? You sort of take away that 4 because I to the 4th is just going to be 1. So I to the 5th is square root of -1. Because going through that whole cycle of 4, you kind of look at like how many times, it's sort of like the remainder, right? Okay. So if the I was odd, it was positive, and if the power is negative. So that's a little, so I is sort of a special case. Okay. So when you're thinking about like what you're asking, or what you're saying, Dom, is like, well, if the power is if the power is even versus the power being odd, that's if you're just raising a negative number to a power, not if you are doing I. So if I had -2 to the 3rd, right? -2 to the 3rd, since this power is odd, it would be -2 times -2 times -2. Times -2 times -2. So -2 times -2 is 4. 4 times -2 gives me -8. Okay, but -2 squared, that's just going to be -2 times -2, which gives me +4. So in this case, with these negatives here, the odd power is going to give you a negative answer, and the even power is going to give you a positive answer. Okay. All right. So let's just kind of let's go back to I a little bit, because those power questions will come in. Okay. So let's see. Oh, Dom, where did it go? Or not Dom. Dom didn't ask this. Let's see. Okay. So 2I I minus 3 plus 6I squared. Okay. All right, so I'm going to rewrite this. 2I minus 3 plus 6I squared. Okay, so we've got this. All right, so 2I, we can't really do anything with that yet. Now 3 plus 6I, we can multiply those two together. Logan, I can do quadratics if you give me a little bit more information about what you want with quadratics. Are you graphing? Are you solving? Are you factoring? What are you doing with quadratics? Okay, so 3 plus 6I squared, that is a binomial. So we are going to multiply those together because they are squared. So we've got 3 plus 6I times 3 plus 6I. Okay, so we're going to FOIL these together. So 3 times 3 is 9. 3 times 6I is 18I. 6 times 3I is 18I. And then 6I times 6I gives me 36I squared. Okay, now I'm going to leave it like that just for a minute, just while we're kind of going through this, right? Okay, so I've still got my 2I out here, minus 9, nothing happens. 18I plus 18I. I, we can treat it like a variable. So it's just plus 36I. Now the I squared, right? So remember, if we go back to I squared is -1. So 36 times I squared is going to be minus 36. Because 36 times -1 is going to be -36. Okay, so now we are subtracting everything that's in here, so I can kind of distribute the negative, or I can just sort of keep track of it, right? But regardless, what I'm going to let's go ahead and just distribute that negative. -9 minus 36I plus 36. Okay, so once I've distributed that negative through here, so I flipped all the signs, now I'm going to start combining like terms. So I have 2I minus 36I, so that's -34I. And I have -9 plus 36, which would be plus 27. So that's how I would simplify that one there. Okay. Thanks, Cole. What does it mean when the exponent is below the variable? Okay, I gotta start my list, guys. Hold on. Okay. All right, so we got so Logan, quadratics. Let me know what you want with quadratics. All right, sorry guys, I'm just catching up on the chat up there. So quadratics, Marcy, inequalities, are you graphing? Are you solving? Give me a little more information about what level of inequalities you're talking about. Are they compound inequalities? Anything like that? Okay, so all right, so I see polynomials. I see polynomial fractions. I think I get what you're saying, but we'll get into that a little bit. I do not do calculus on here. Okay. Adding and subtracting polynomial fractions. I -1, -1, and you always go by 4. Yeah, that's true. Okay. Oh, so the I squared, I think somebody was asking about that. I squared becomes -1. So you would multiply, it's just 36I squared is the same thing as 36 times -1, which is -36. Okay, sorry, Diana, I just saw your message. Okay, let's see. Brent, let me know what you want about trig. Are you talking about just trig ratios? Are you talking about graphing trig? What are you talking about? A quadratic formula to square root. Quadratic formula to square root. Do you mean like once you get the quadratic formula? You don't even have a name on there, but quadratic formula, like simplifying your quadratic formula? Let me see. Why did I do that? I did subtract 9. When you have the -9 there, so that becomes a -9. So -9 plus 36 becomes 27. So -9 plus 36 is the same thing as 36 minus 9. Okay. Yeah, Sam, it's a pattern. So every 4, so with the I, right? So I is root -1. I squared is -1. I cubed is negative root -1 or negative I. Right, I could write that as the same thing. I to the 4th is just a 1. So if you have, you kind of take the exponent. So if I had something like, well, so like I to the 5th, right? 4 goes into 5 one time, but it has 1 remainder, right? So it's going to go through all this, and then it's going to go back to the beginning. So I to the 5th is just I. Okay, I to the 6th would be -1. And the reason for that is because 4 goes into 6 one time with remainder of 2. So it would go through this whole thing, 1, 2, 3, 4, 5, 6, and it's -1. Okay, so if I had like I to the 14th, right? So I to the 14th, I would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, it's -1. Okay, so again, it's all based on that pattern. So you could also look at it, well, how many times does 4 go into 14? Well, it goes in 3 times. How much is left over? 2. So that means that it's technically just like I squared. So it's -1. Okay, so the whole the powers of I, it's really confusing. Like if you're just joining us, that is a lot of 1s and a lot of radicals, right? But what it really is it's just that pattern, right? It's just going through these 4. It's sort of a loop. It's going to keep repeating itself, right? Okay, we're going to talk about I a lot. Okay, let me see. You did it outside the parentheses and not inside the parentheses. With the -9, with the -9 here, I just distributed that negative. I could have also just said, okay, 2i minus 36i is -34i. And I could do like -9 plus minus -36 is 27. That's a way more confusing way to explain it. Whoa. Okay, so that's why I kind of think about it as like distributing that negative, if that makes sense. Okay. Yeah, this is more by multiples. Sorry, this is more like this is like algebra 2-ish. Yeah. Oh my gosh, Sassy, I'm glad you fixed that. I saw your multiples of 5 and it completely threw me off. And I was like, no, it's 4. Okay. How many people will use this in a real life situation? This in particular, probably not a lot. But you know what you do use in a real life situation is logical reasoning and pattern recognition. You're going to look for a pattern and you're going to find it, right? You may never have to deal with the roots of I ever again, but you may want to paint a pattern onto your wall. You got to keep track of how many times it repeats, right? Looking at wallpaper, hanging wallpaper, right? These are things, or like with gardening, right? These are all things that you want to be able to recognize with patterns. You're building something. You want to be able to look for a pattern, use measurement, right? Things like that. Those are all different these are all different things that you can work on, right? It's critical thinking, it's problem solving, it's figuring out what to do when something's a little bit difficult and using what you know to solve for what you don't know. That is life, right? Problem solving is everywhere, okay? All right. Okay, so trig ratios. Oh my gosh, I've got some students taking a test on, algebra 2. I've got some students taking a test on trig tomorrow. Okay, so let's see, we did that. Let's do some trig ratios, sure. Okay, so trig ratios, I love trig ratios. So trig ratios are generally based, not generally, they are based. Usually you learn them first with a right triangle. Okay. So one of the very beginning things that we learn about right triangles is Pythagorean theorem, right? We've got a squared plus b squared equals c squared. And that sort of forces you to realize that, like, you can't just pick any three numbers and make them a triangle, right? You can't have like a triangle with a side of 1, 2, and 45, right? That little tiny 1 and 2 are not going to fit all the way to 45. It's not going to work, right? So you start to think, okay, so there's a limit to these triangle lengths, right? So for example, 3, 4, 5. So 3, 4, and 5, that is a Pythagorean triple. They are going to work out this way. I can make a right triangle with a side length of 3, 4, and 5. Okay. Now, this will work with any set of three numbers that fit within the Pythagorean theorem. Okay. So as long as they fit within the Pythagorean theorem, they will make sides of a right triangle. Okay. Now, what's interesting though is that every right triangle, like I said, there's sort of like a finite number of right triangles, right? There's not an infinite number. There's a finite number because they have to fit within that Pythagorean theorem, right? Yeah, 3, 4, 5, 5, 12, 13, all of that, okay? Now what trig does is it takes it kind of like one step further and it says, not only do they fit in with the Pythagorean theorem, but also they are going to be set in specific ratios, okay? So many times what you'll learn first before you really dive into trig, or you may learn it and you don't even realize that you know it, is special right triangles. Okay, so a special right triangle is something where, like, if you have a 45-degree angle here, and this is a 45-degree angle here, the way that these sides will always line up, always, no matter what, is that this side and this side will be equal. Okay, so we just say they're A. Okay, so A and A. And out here, this is always going to be the side length, where it takes the side length times root 2. That's how it's always going to work out, okay? So we've got 45, 45. These sides will always be the same. They're always going to occur in that ratio, right? 1 to root 2. Okay, or to 1 root 2. It's the same thing, right? So 1 to root 2. It will always be in that ratio. But these are special right triangles, but like I say all the time, special right triangles, they're not that special. Okay? They're not that special. They're kind of special, but not really that special. Because all right triangles actually exist, and all triangles actually exist with these very specific, with these very specific ratios. So it doesn't matter this is 45 and 45. Any triangle I can actually do with these specific ratios. And those specific ratios are what we call the trig ratios. Okay? Now the big three, SOHCAHTOA. Okay? Big three is SOHCAHTOA. So it is sine. Okay? Sine, let's say this little circle with the line through it is called theta. Okay? So sine of theta is the relationship between this side, which is called the opposite, and this side, which is the hypotenuse. Okay. So the sine of a specific angle, the sine of any angle is always going to be the same ratio. Okay. So if this is a 32-degree angle, it's going to have a specific ratio between the opposite and the hypotenuse. Okay. If it is a 27-degree angle, it's going to have a specific relationship, specific ratio between those two, okay? It doesn't matter what that angle is, but that opposite and that hypotenuse, they will always be in the same ratio, okay? Another one is it's relating this side, which is called the adjacent, and that is called cosine. So cosine theta is the relationship between the adjacent and the hypotenuse. Okay, and again, so if I have an angle of 27, this ratio, cosine, the ratio between this side and this side of a 27-degree angle is always going to be the same. It doesn't matter how large or small the triangle is, that ratio is going to remain the same. Okay, and then the last one that relates the two sides that we haven't paired up yet is tangent, which is the opposite over the adjacent. Okay, so these are the big three. This is where SOHCAHTOA comes from. So SOHCAHTOA. SOHCAHTOA. Okay, so the opposite is always the one that's across from the theta. Okay, so if I moved my theta up here, now this one is my opposite. Okay, hypotenuse is always hypotenuse. Hypotenuse is always the longest leg, and it's always across from the 90-degree angle. Okay, so we have sine, cosine, and tangent. Now we have three other ratios that are like not opposite, they're inverse. Okay, so the inverse, we have the inverse of sine is cosecant. So that's going to be the hypotenuse over the opposite. And then we have secant theta, which is the inverse of cosine. So that's the hypotenuse over the adjacent. Then we have cotangent. Kind of ran out of room here. Sorry about that. It's the adjacent over the opposite. Okay, so these are the 6 trig functions. And again, depending on what your angle is, your sides will always, always, always occur in that ratio. Okay, so we have the adjacent is adjacent to the theta. Okay, so it's making up part of the theta angle. Okay, the opposite is across from the theta. The hypotenuse is always going to stay the same. So again, if I had my theta up here, this would now be my adjacent, and this would now be my opposite. Okay, so we've got a lot of relationships between the angles and the sides. So most of the time when you're first learning triangles, right, you're going to first learn a triangle with like you've got the angle, you're dealing with the angles or you're dealing with the sides, right? So you know that angles all add up to 180. You know that the side lengths, if it's a right triangle, you can use Pythagorean theorem, okay? But if it's not a right triangle, or if you don't have like perimeter or any sort of things, you're kind of screwed, right? You can't figure out the side lengths of it until you start getting into trig. Trig, you can start using this anytime, right? You can start solving any triangle that you have, okay? So if I say, here is my triangle, okay? And I'm going to say that this is theta. Okay. And let's say that this side is 8. And this side is 15. Okay. How did I know you were doing this right now in math? It's kind of that time of year. I feel like anybody who's in like an algebra 2 or integrated math class, like sophomore, maybe junior year, but probably sophomore, even freshman year. Here we are, 10th grade, it's trig season, baby. Okay, so here, I know it's a right triangle. Now, what you may be asked to do is something that I always ask my students to do, which is to solve this triangle. Solve this triangle! Okay, so I'm gonna, I guess in order to name the triangle, I have to actually write down the vertices, right? Okay, so we've got A, B, and C. That's kind of hard to see. Okay. So to solve a triangle means I'm going to find all of my side lengths and all of my angles. Okay, now right now I only have 2 side lengths, right? And I have 1 angle. Technically it's the right angle. I get it. Okay. How do I find that missing side? I don't actually have to use any special trig or anything. Like, I can just use Pythagorean theorem, which is going to be my next tattoo. I got to figure out how to make it look cute and pretty. Okay, so to find that third side, right? So this would be side A. Okay, so side A is going to be, I'm just going to use Pythagorean theorem. I'm going to do 15 squared minus 8 squared. Now I know A lot of you may be saying, but Sarah, the Pythagorean theorem is a squared plus b squared equals c squared. I know, but I have the hypotenuse. So if I know that this squared plus this squared equals this squared, then this squared minus that squared must equal this squared. Okay? Just a little shortcut. Okay? So I'm going to use my numworks calculator because it simplifies radicals for me and it's amazing. Hashtag not sponsored. Okay, so we've got root 15 squared minus 8 squared is, oh, I didn't even need to simplify it. It is root 161, okay? Now, usually when I'm asking my own students to solve triangles, okay, I would say round this to the nearest 10th. When you're finding side lengths, you round to the nearest 10th, okay? And so we get 12.7. Okay. And then for angles, I'm going to write this. For angle measures, we would round to the nearest whole angle. So this is 12.7. Okay. So now to make the connection between my side lengths and my angles, because I need to figure out what this is. Now I do know that they both add up to 90, right? Because 90 plus this will all equal 180. So now I need to go in and I need to use my trig ratios. I have all three sides. I can use any of the three. This is a calculator called a numworks calculator. It's amazing. Okay. So I can use any of my ratios. I can use any of my side lengths for my ratios, but I'm going to stick with 8 and 15 because I know I already rounded this. So the more you round in each problem, the further away from the actual answer it gets. So I try to always just stick with what I'm given, or I would use exactly root 161 if I were doing any sort of calculation, right? But when I'm giving my answer, I can say 12.7 is fine. Okay, so I'm going to say, so I've got my 8 and my 15, and I'm going to set that as my theta. So this is my adjacent, and this is my hypotenuse, okay? I could use this for theta. I can use this for theta. It doesn't make a difference with your answer. It only makes a difference with what ratio you set up, okay? So again, I can use my angle here, or I could use angle A or angle C. It won't change the answer that I get for my angle measurements because my angle measurements are what they are. It will change which trig ratio I use, okay? So I'm just going to use angle A, and actually I'm not even going to call this theta. I'm just going to call it angle A, but I'm focusing on this one. So here, if this is angle A, I've got my adjacent and my hypotenuse. So I'm going to use cosine, right? So ka toa. So ka is cosine. So I'm going to do cosine of A equals 8 over 15. So adjacent over hypotenuse. So it's 8 over 15. Okay. Okay. So the reason I found the other side length, right, it seems kind of silly, but it's because it's asking me to solve the triangle. And so could I have found the side length next? Yeah, I didn't have to find the side length first, right? I could have found the angles first. It doesn't really make a difference. I have to find everything, so the order doesn't really matter in this case, right? So cosine of A is 8 over 15. Now I've got a little bit of a problem, right? Because I don't know my angle measurement. So when you look at your calculator, okay, to sort of get rid of that cosine, we use something called it's called arc cosine or inverse trig, okay? Because if I wanted to get A by itself, it's sort of well, can I just divide by cosine? Not really, because it's a function, but I can do cosine -1. So I would have A equals cosine -1 of 8 over 15. That is going to get me my angle measurement. Okay, now that cosine -1 is usually if you're using a TI like this, you would do second and cosine, it's right above it. If you're using a numworks or even a Casio, oh, I think I left my Casio on my desk, shoot. But numworks, you would do the shift and cosine, and it calls it arc cosine, is the same thing, okay? And then, let's see. So we've got cosine -1 is 8 over 15. So the angle A is approximately, because we are going to round it, 8 over 15 is 57.76. So that rounds up to 58 degrees. Okay. Now, if angle A is 58 degrees, 12 got erased. If angle A is 58 degrees, and these three need to add up to 180, I'm going to do 180 minus 90 minus 58, and I get 32 degrees. So I know that angle C is approximately 32 degrees. Okay, now I'm saying it's approximately because I know I rounded 58, so I'm going to round also. I know 32. It's not exactly 58 degrees. It's not exactly 32 degrees, but it is really hard to work with like fractions of a degree. It's really hard. You can't even use the parabola. You can't even use a protractor to do that. Okay. All right. So let's see. I love this math too. This is fun. And guys, I will tell you that this math trig was so hard for me to understand when I was in high school. Like, I struggled so much to understand this. And looking back on it now, I think I was just overcomplicating it and just not practicing, just being like, nah, I don't get it. And just walking away, right? But the thing is that, you know, if I could go back and talk to little like 15-year-old Sarah, like let me tell you what you're going to be doing someday. And she absolutely would not have believed you. I would have believed you that I was going to be a teacher, but not a math teacher. Long story short, I appreciate when you guys are saying like, oh my gosh, this is so much easier. Like, she's explaining it so clearly. Like, that, those types of comments are really mean a lot to me, because I struggled so much to understand it. And once I was able to kind of realize like, oh, it's not that hard. You're just scared of it. Like, I feel like that was a big revelation for me, that it was like, it's not that hard, but you do have to practice, right? You do have to practice, and don't be scared of it. So that's why I'm here doing this, is because, you know, I don't want anybody to be scared of what they're doing in math. Can I do proofs? Can I? Yes. Will I? No. But I can walk over proofs. I can walk through proofs. Proofs are basically just making these logical steps and justifying every single step with a walking through logical steps with like justification with number properties and things like that. Why didn't I use law of sines if I had a known ratio? So with the law of sines, so I did not bring up law of sines because we were mainly focusing on just using trig ratios to start with, but we can do law of sines. Now law of sines, I guess law of sines, you could have used law of sines to do this one. But that probably would not have been my first instinct personally. Not saying that it's wrong, because again, the triangle is the triangle, right? When you're saying solve a triangle, you solve the triangle, right? Do I make students show work? Yes, I do make students show work, but I try to shy away from the whole phrase of like, show your work. I say like, justify your thinking or show your reasoning. Because I think like there are some things where it's like, literally, I know what to put in my calculator, so why do I have to show my work? I didn't do any work, I just put it in the calculator. So I prefer kind of saying like, show your reasoning or justify your response or justify your answer. And that I explain it to my students, like, if you just typed it into the calculator, it's not wrong, but just like, can you at least write down what you put in your calculator? Like, just so I can have some semblance of how you solved it, right? Okay. Let's see. So law of sines, let's do law of sines. So law of sines is another kind of like way of figuring out a triangle, and it is primarily used in non-right triangles. So this is really interesting because if you've got a non-right triangle like this, okay, and actually, hold on, I have to process something really quick. Okay, if we do, yeah. So with the law of sines, I didn't want to get into the ambiguous case. We're not quite there yet. So if I say that this is 42 degrees, okay, again, this is not a right triangle. This side is 12, and this side is 18, okay? So here we go. Can we solve this triangle? If you don't know trig, no, you can't. Okay, you would know the range of this side length, right? The range of this side length. But actually, well, actually no, because with the angle there, it is locked in. Okay, so with the angle being there between these two sides, it is locked in. I cannot change anything about this third side. There's only one way to complete this triangle. So this is where the law of sines comes into play. So the law of sines is where you have the ratio. Well, I'll do ABC again. Okay. Now, when you're talking about these sides, so the angles are capital letters. The side lengths are the lowercase letter of the letter across from it. So this is angle A with a capital A. This is side A with a lowercase a. Okay. So the sine of angle A over the side length of A. Okay, so that ratio is going to be the same for every single sine angle and related to the side. Okay. Okay. And you can also flip this if you need to also, right? You can have sine A over A, or you can have A over sine A. As long as, obviously, as long as you flip all of them, right? So you can have the sine of the angle over the side equals the sine of the angle over the side equals the sine over the angle, sine of the angle over the side, or you can have it flipped upside down, okay? All right, so we are going to fill in what we know, okay, and solve for what we don't know. Can we do this? Ooh, I've set myself up into something that's not great because I do not have a complete pair. Okay, so we got to do some changes. So I'm going to do... I can find the area of this. SAS. Because I don't have a complete pair. Hold on. Okay. I'm hoping that this won't get into the ambiguous case. Stand by. Need the little, like, beep.
Beef Stew says you have the same haircut as their geometry teacher, and they love it.
It's in the blood. Okay. Sorry, guys. I made an oopsie, which I do sometimes. Okay. We'll leave that one as 12, and then we'll make this one across here 10. Okay, sorry about that. I don't think that'll be ambiguous case. Okay, so here we've got this 42 degrees, 12, and 10. Okay, so with the law of sines, so the problem what I had before was that I didn't have a complete ratio. So to use the law of sines in this way, in this application, we do need to have a complete ratio or have enough information to find the complete ratio, right? So I'm going to set this up. I'm going to set it up with what I know. So I know that sine A over A is going to be sine 42 over 10. And I also know that it is the same as if I looked at the sine of angle C over 12. Okay. So now I've set this up here. And again, remember, this is what was wrong with my first set of values, is that I didn't have a complete ratio here. Okay. So now I've set this up, and proportions, even if you are not in algebra, even if you are nowhere near trig right now, I'm gonna guess that if you're here, you probably remember or know how to solve a proportion, which is where you cross multiply, right? So we're gonna cross multiply here. Yes, I know there are other ways to solve proportions, but we are gonna stick with cross multiplication, okay? Because that is the most typical way that people learn how to do these. So a lot of times I know people get upset when I don't solve a problem in a specific way, or why are you doing it that way? It's too long, it's a much shorter way. I am working through these problems in a way that I'm hoping that will appeal and make the most sense to the majority of you watching. So it's not always the most efficient way, right? There's other ways to do it. And usually after we get through the problem, I kind of go back like, okay, now here's how you could do it in like 2 steps, okay? But while we're working through these, I want them to be, you want to make sure that people are able to kind of like get into it a little bit. So here, if there's like a 6th or 7th grader watching that says, wait a second, I know how to solve a proportion. Like, I didn't know that was going to come up in trig. It does. Proportions never go away. Okay, proportions and fractions, they're here to stay. Okay, so here I cross multiply, and when we solve a proportion, right, we've got cross multiplying here. Somebody said I thought 10 would be somewhere else. Sine 42 over 10 is because sine of this angle it's the ratio between the sine of the angle and the opposite side, or the corresponding side, right? It's the side that's across from it. So that's why sine A over A, you've got sine A, which is 42, over side A, which is 10, okay? So I've got, let's see, 10 times sine C, oh my God, equals 12 times sine 42. Okay? Again, it's a basic proportion, right? Okay, so we're going to divide by 10. So we have sine C equals 12 sine 42 over 10. Okay, sure, you may be tempted to kind of like simplify that 12 to 10. You don't need to worry about it. It's fine. Okay, so then, and then we're trying to find the angle measure. So remember, we use that inverse trig, right? We use that sine -1. So the angle C is going to be sine -1 of 12 sine 42 over 10. Okay. So we're going to go, So we're going to go sine -1 of 12 sine 42 divided by 10. And that gives me approximately, for angle C, it gives me 53.4133839. So I'm going to leave it as 53 degrees. Okay. So side C is approximately 53 degrees. Okay. So now we've got another ratio that we could work out with. What we also have is we've got 2 of our 3 angles in a triangle. So can we figure out what angle B is? Yes, we can. Do we need trig? No, we don't. So we know 2 of the angles. We know they're all going to add up to 180. So we do 180 minus 42 minus 53, which is 85 degrees. So my longest side in my triangle is side B, which is down here. Okay, that is 85 degrees. So now what I'm going to do, so I'm going to set up my last ratio. I'm just going to write this on the grid side. Okay, my last ratio. And again, remember I talked about how I like to use the information that I'm given because I know that this is rounded, right? I know 53 is rounded, so I'm going to go back and just use the sine 42 over 10 because I know for sure that that is not rounded. So sine 42 over 10 equals sine of 85 over little b, which is this side. Okay. So let's see. So I've got b. So again, it's a proportion, right? We got two ratios. We're going to cross multiply. So we've got b times sine 42 equals 10 sine 85. Divide by sine 42, because sine 42 and sine 45, whatever sine of a number is, it is an actual number. Like it is an actual value, right? Like you can type it into your calculator, you can get a big ugly decimal, but so now we've got b equals 10 sine 85 over sine 42. And this I can just type into my calculator. So I've got 10 sine 85 divided by sine 42, which gives me approximately 14.88789. So I'm going to say it is approximately 14.9. Okay, now I always ask myself, does this make sense? Right? Well, the smallest angle is across from the smallest side. Mediumest angle is across from the mediumest side. Largest angle, longest side. Makes sense? 10, 12, 14.9, those are in a realm of possibility for triangle measurements, right? If I had 10 and 12, my range of values would need to be, it's between 2 and 22. Okay, so 14.9 fits right in there. And that's how we can use trig to solve a triangle. There we go. Okay. All right, I have, so what math is this? This is trig. This is trigonometry. It's usually done around with like algebra 2. Sometimes people might say that it's algebra 1. Totally fine. Yeah. A lot of times even like 8th grade students will learn this because it can sort of stand alone and it's fun. It is sort of fun. And so multiple, like more exposure is always going to make you more comfortable with it when you see it in a more like advanced math setting. Okay. All right. So yeah, geometry, it could be in geometry too. A lot of times you'll use it in geometry to maybe find an angle measure on a coordinate plane. Okay.
You're getting a lot of questions. People freaking out about the SAT
tomorrow. Ooh, SAT tomorrow?
Well, tomorrow
it's a
Saturday.
Friday. But I guess if you're offering it at your school. So with the SAT, remember to use your formula sheet, right? And on your formula sheet, it does have the special right triangles. I don't know if it has trig ratios. Let's look it up. Let's see. I feel like it could go either way. I feel like it's not, but let's see. So the formula sheet is always going to give you all of those things. I don't think it does give you the trig ratios, but I know it does give you those special right triangles, which is really nice. It gives you those special right triangle ratios. Keep in mind that the SAT is, they want you to kind of puzzle through some things. So they're going to give you some weird questions. But if you are in like algebra 2 or trig or something beyond, keep in mind that the vast majority of SAT and ACT questions for math are going to be from like your algebra 1 and algebra 2 lessons and geometry, right? There's going to be some trig on there. Mostly it's just going to be right triangle trig. It might be law of sines, but a lot of times when they ask you a law of sines question, they put the law of sines on there. Like they'll put like a little reminder like, hey, we've got your, oh, I got my inactivity thing. Why is that saying that? I was just doing all that. Okay. Yeah, so SAT and ACT, it's all kind of the same thing. There's some slight nuances in like how they, like I think it's, I can't remember. I gotta find out from John Lee what he said about the SAT and the ACT. One of them, I can't remember which one, but it's sort of like, it's all kind of scattered. Like you may get a really complicated math problem and then a really easy one, a really complicated one. And then there's the other test is more like it builds up to the most complicated. I want to say that it's SAT that builds up to the most complicated. So like the back end of the problems, like don't spend as much time on like spend the majority of your time on the first 20 or however many. Okay, is that the ACT?
Yeah, the SAT kind of is like a guide.
But now it's all digital too, and so I don't know if, most of them are digital now, so I don't know if it's dynamic.
Right, so it's like dynamic, and they'll go like, oh, you got this hard one right, so we're gonna give you more hard ones. Mm-hmm. And if you get the hard ones wrong early, then they send you down a path of easier. Right,
so that's kind of going off of like the old paper tests. It was a little bit more kind of like you could sort of pick up on the pattern. Okay, so circles, let's see. Circles in geometry, quadratic formula. Okay, so the quadratic formula, I can do a quick quadratic formula. So quadratic formula is everybody's favorite song. It's a real banger. It is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now all these a's, b's, c's, squared, square root, plus or minus, what in the world does it mean? It's looking at, when you're looking at a quadratic, you've got ax squared plus bx plus c. So when you're solving these quadratics, which is in this form, right, where you just have like x squared, when you're solving these quadratics, let's say this equals 0. Okay, if you're using the quadratic formula, it does have to equal 0. So when you're doing the quadratic formula is sort of a shortcut of just using these coefficients to solve for x. Now, x in this case, when you are solving a quadratic, it is where the equation equals 0. So the x value where the whole equation equals 0, that is what you call the solutions, or they're also called like the roots. Okay, but it's basically where every quadratic, I mean, generally speaking, the quadratics are going to look something like this. Okay, they're going to be a little parabola like that. And so your solutions, or your zeros, or your roots, they're all the same thing. They are here at your x-intercepts. Okay, so everybody's all about the y-intercept when you're graphing lines, but when you get into more advanced equations like polynomial functions and quadratic functions and all of that, it becomes all about the x-axis, the x-intercepts, okay? So when I have something like this, usually you're going to use this, you're going to use the quadratic formula on a quadratic that doesn't factor. So that's what we're just going to kind of go for, is that we're going to say, so we've got 2x squared plus 5x minus, I almost gave you one that was factorable, but we'll do minus 2 equals 0. Okay. Yeah, that one's not going to factor. Negative 4 plus 4 minus 1. No, that won't factor. Okay. So our A is 2. Our B is 1. Yay, John Libera. He's here. Okay. And then negative 2. Okay, John, you just, oh, well, I didn't even sing the song. Oh, I know. I didn't even sing the song. Okay. All right, so we've got 2x squared plus 5x minus 2 equals 0. So our A is 2, our B is 5, and our C is negative 2. So now we just plug it in and solve. Because this is going to give us our intercepts where it crosses the x-axis, right? Okay, so we're going to go, and we'll sing it this time, but I'm going to fill in the numbers as I sing it. So we go x equals negative b plus or minus, I can't sing it and write the numbers. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. X equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Ha ha. All right. Okay. It's just like Pop Goes the Weasel. Okay. All right, so now we're going to start simplifying. So I'm going to start with what's underneath here, which is called the discriminant. Now, there are ways of using the discriminant to figure out, like, how many solutions are there going to be, how many real solutions, blah, 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 blah. I just kind of go for it. So we have negative 5 plus or minus. The reason we have plus or minus is because we're dealing with a square root. So the square root of 25 minus 4 times 2 times negative 2, that ends up being plus 16 over 4. Okay, so I'm going to simplify all of that out, and it gives me negative 5 plus or minus the square root. Let's see, 25 plus 16 is 41. That does not simplify, over 4. So this gives me my two solutions. These are my two spots where it's going to cross the x-axis. So it's going to be at negative 5 minus negative 41, or I'm sorry, negative 5 minus root 41 over 4, and it's going to cross at negative 5 plus root 41 over 4. Okay, so that's what it is. So factorable or unfactorable. So factorable means you can factor it. And this is going to be the last bit before we sign off. So with that one up there, so 2x squared plus 5x minus 2. Now, looking at these solutions, I know that it's not factorable. But if I gave you like this, 2x squared plus 5x plus 3 equals 0. Okay. So 2x squared plus 5x plus 3. So I can factor this. The way I know I can factor this is because if I take, and again, we got into factoring last week. We get into factoring every week, I feel like, which I love it. But we take 2 times 3, which is 6. And we're going to look for two factors that multiply to 6. So like 1 and 6 and 2 and 3. But we need them to also add to 5. Okay, so that would give us 2 and 3. Okay, so then if we factor this, we're going to split 2x squared plus 2x. This, again, this is just how I do it, how I teach it to my students usually. Okay, sometimes we'll do the box method. Sometimes we'll do all these other ways of doing it. There's so many things. There are so many different things or so many different ways that you can factor. So I factor by grouping. I take a 2x out of here, and I'm left with x plus 1. I take a 3 out of here, and I'm left with an x plus 1. And then those are my two binomials. So being factorable means that I can write it as two things being multiplied together. Okay, so 2x plus 3 times x plus 1. So what that means is that either, now we can use something called the zero product property, which means that if I've got two things multiplied to equal 0, one of them has to equal 0. So either 2x plus 3 equals 0 or x plus 1 equals 0. Either one. Okay, so 2x plus 3 equals 0, that means x could be negative 3 halves. If x is negative 3 over 2, then it would be 0. Or if x equals negative 1, it would be 0. So that means that my quadratic is going to cross at, let's see, x equals negative. Ooh, these are going to be very close together. It would be something like this. Okay, very close together because we've got it at x equals negative 1 and x equals negative 3/2. Okay, so that's what it means to be factorable, is that it's going to lead to these nice real and rational numbers. Okay, this is not like 5th grade math. This is definitely not 5th grade math. Okay, this is it's sort of like reverse distributing. This is probably I mean, 9th and 10th grade math is when you really start doing all of this. Yeah, freshman year, this is totally right on track for freshman year, even 8th grade year. Sure, some of you may be learning it earlier, but the vast majority of people are going to be learning it in like 8th, 9th, and 10th grade. All right, guys, it is about that time. So Anna's review, it never goes away. It never goes away. It's going to keep on coming up. All right, so have a wonderful night, a wonderful evening, and I will see you guys next week for Math Thursday. Bye.